MGF is a simple trick to make positive random variable, which use a non-negative and strictly increasing function pi. Okay. So because Markov inequality require non-negative random variables, when we use such exponential function, the pi function, we can make any random variable to be non-negative. Okay, so with Markov inequality, the probability x is strictly greater than or equal to a is less than or equal to expectation of exponential zeta x over expectation zeta a. So I omitted the intermediate step. This probability is equal to probability exponential of x greater than or equal to exponential of a, because exponential function is strictly increasing, and thus the probability x greater than or equal to a is equal to probability exponential of x greater than or equal to exponential of a. And from the Markov inequality, we have this inequality. The exponential function with any positive constant zeta still keep this very nice property. So more generally, we can write down this inequality with any positive a and parameter zeta. This is also known as Chernoff bound. So the Chernoff bound is this. We use Markov inequality and MGF function trick. MGF function has very nice two property. First one, this is non-negative. The MGF function can make non-negative random variable, and MGF function use strictly increasing function. So this is very nice to show, nice to find a nice upper bound for this property, probability. Okay, sorry. But here, the MGF function has one more important property. The exponential zeta x, when you look at this function, the value increases very fastly as x goes to infinity. So at the tail area, this function increases very rapidly, which makes your PDF of this new random variable y becomes very right tail. Okay. In the Markov inequality part, I explained that when PDF has very right tail, like this, the probability for this area very concentrated on this left-hand side extreme point, and the probability for this area also very concentrated here. And Markov inequality is tight when your distribution have two Dirac delta function very concentrated at point 0 and at point our target boundary A. So essentially, with very right tail PDF function, we have such nice property such that the Markov inequality becomes tight. Okay, so that's why many concentration inequality love to use MGF3. So Chernoff bound is the most famous bound that leverages such MGF property like this. So probability x greater than or equal to a is less than or equal to infimum zeta for the area theta, for the theta strictly greater than 0, expectation of e to the theta x over e to the theta a, which is equal to this because we assume that every random variables are independent. So exponential set x, and x is sum of independent random variables. We can rewrite this expectation as product of expectation of e to the theta xi, and this is the MGF function of each random variable xi. Okay, so using this property, using MGF, we can find the probability x is greater than or equal to a. This theorem is called Chernoff-Hefting's inequality. For the case the random variable x1 through xn be IID Bernoulli random variables with probability p. Then for any q bigger than p, we have this concentration inequality with KL divergence between q and p. For the case q is less than or equal to p, we have the other side of concentration inequality, the summation xi less than or equal to nq, which is less than or equal to exponential minus n KL divergence q and p. So here the KL divergence dqp means q times log p over q plus 1 minus q times log 1 minus q over 1 minus p. Right, so let's show the Chernoff bound. So from the Markov inequality for all theta, of course positive theta, we have this first inequality. Okay, first use MGF trick. We have this first inequality, and since xi is IID Bernoulli random variable, we have this and this equality. So from the independence property, the summation inside exponential becomes product of exponential e to the theta xi. And from the fact that xi is randomly sampled from Bernoulli random variable, Bernoulli distribution with the parameter p, the xi is equal to 0 with probability 1 minus p, and xi equal to 1 with probability p, so we have expectation p times e to the theta plus 1 minus p. Right. Then, what was Chernoff bound? Chernoff bound compute this fraction and then find the infimum, right? Find the minimum value over whole theta, which is non-negative, positive. So what is the optimal theta that minimize this part then? From the first derivative of this theta function, we can find the derivative is equal to 0 at point log q 1 minus p over p times 1 minus q. And so when you replace theta by this specific value, we have this concentration inequality. Okay, the other inequality we can show as well in the same way.